残酷な天使のように少年よ神話になれ青い風が今胸のドアを叩いても私だけをただ見つめて微笑んでるあなたそっとくれるもの求めることに夢中で運命さえまだ知らない痛いけな瞳だけどいつか気づくでしょうその背中には遥か未来目指すための羽があること残酷な天使の手で窓辺からやがて飛び立つほとばしる熱いパトスで思い出を裏切るならこの空を抱いて輝く少年よ神話になれ。
Oh, hello! Today we won't be talking about math. Instead, we'll be talking about this book I bought at a thrift store called My Thoughts Exactly that has a picture of a cat on it. Okay, so now that we've got the idea of even and oddness and how it interacts with integration pretty well sorted out, we've done a couple of examples. It's not too bad. Let's start to talk about the next concept here. So, we know that the definite integral, the integral from say a to b of f of x dx, measures the net area of the region bounded by a function and the x-axis. So let me sketch this really quick for us here. So, terrible line, what the heck? Alright, let's just do ourselves a quick little picture. Okay? So maybe we're going from A here to B here. I'm just going to sketch some nice, easy looking function. I don't know. There we go. Something like this. This is y equals f of x. There we go. And if we're looking at the area, the whole gist of it here, we don't even need to care about net area in this example. As I'm drawing it, it just looks pretty nice and easy to deal with. So, okay, we're dealing with the area here. This is just, let's call this area A. It's the definite integral from A to B. It's all it is, of f of x dx. And there we go, we got some number A. That's the area. So the gist of what's going on here is that we can make a rectangle that has whatever area we feel like. All right, so if I switch to another color here and I start to sort of draw the picture, basically think of it like this. What I'm going to do is I'm going to take a rectangle whose base is the exact same as that interval, and what I'm trying to figure out is how high does this guy have to be to have the same area. So maybe something a little bit like, I don't know, like, I'm going to not quite draw that right. Let's see. I don't know, something like this, maybe. Maybe this guy here sort of seems like it has something in the vicinity of the same area. Okay, but what should this height be? H. Seems a little bit weird. What we know is that the area of this yellow rectangle here, as I've sketched it, what it has, this guy's area is H times b minus a, since this distance down here is just b minus a. Okay, b minus a times h, that gives me the area of this thing here. Maybe I should use a slightly different color to point at that, since that's sort of hard to see. There we go. Area of that guy is h times b minus a. So what I want is h times b minus a to equal a, the area under the curve. Okay, so this is just, as we said, the definite integral from a to b of f of x dx. So we just have to solve for h. If h times b minus a is equal to the definite integral from a to b of f of x dx, this says that h has to be equal to, well, 1 over b minus a times the definite integral from a to b of f of x dx. So notice something nice going on here. Now there's kind of a lot drawn on this little picture here, but basically the important part of this is that, and let me kind of turn down my opacity on this there, this rectangle is grabbing a little bit more than I need. It's not a very good color to use. This rectangle is grabbing a little bit more than I need up here. It's missing a little bit over here, and it's missing a tiny piece right there. Oh, I'm picking a very terrible color. Here, let me even just use, there we go, straight up white. That'll be better. Missing a little bit here, getting a little bit too much up here. I'm missing a tiny piece right in there, maybe a little tiny piece over in that corner. But somehow, if I had drawn this really perfectly, I would be balancing all of these out. That is, the part above that I'm missing and the parts below, these guys should all equal each other. The extra pieces of area in the rectangle here, and the parts outside the rectangle, those two guys, but still beneath the curve, these guys should equal each other. Somehow what we're seeing is that this height here is giving us information about an average, and intuitively this sort of makes sense. If we're trying to balance out, the parts that are really low on the graph of this function on this interval and the parts that are really high, drawing a line dead through the middle is sort of giving us an average, yeah? It's like the closest line to what the function's doing here overall. The parts where the function's greater are balanced out by the parts where the function is smaller. This makes sense. This is good. Okay, so this is the idea of the average value. That is, what we are looking at is the height of a rectangle. So the width of the rectangle is b minus a, the length of the interval. The height h is such that the area of the rectangle is equal to h times b minus a, and if we're setting that equal to the integral from a to b of f of x dx, we get that the height is just 1 over b minus a times the definite integral from a to b of f of x dx. We're going to call this height, the height of this rectangle, we're just going to call it the average value of f on the interval ab. This is the definition. So the average value of an integrable function f on the interval ab is just 1 over b minus a times the integral from a to b of f of x dx. Basically the gist is that area is, kind of archetypally, it's like width times height. And so if I divide by width, that's what this 1 over b minus a is. I'm getting height. And since my height is changing, the static value I get back is something like the average. Just in the spirit of economics, we normally refer to this as f bar. The average is f bar. And the bar just comes from the fact that we have a division here, dividing by the length of the interval. So the bar kind of is saying like we're averaging it, we're dividing by something. So f bar, the average value of the function, is just the height of this rectangle that has the same area, net area, as the definite integral of the function on the interval. Okay, cool. Let's do an example and see what's really going on. Okay, another good example. Let's get used to this idea of average value of a function and see how it's kind of useful in a lot of ways. So the gist of it is that we could look at something like elevation, like the average elevation. How do they calculate the average elevation of a state? The elevation of a state varies kind of like a hell of a lot across the entire state. But we can say things like, oh, I don't know, Wyoming has an average elevation of X feet, right? Some number. I don't know what it actually is. It's probably pretty high. But yeah, so you can do that. How do they do it? Here's how. So suppose we have a hiking trail that has an elevation given by something like f of x is 60x to the third minus 650x squared plus 1200x plus 4500. So gist of it is that we got, I don't know, we got some kind of like a mountain and we got like a little, trail up on it or something. I don't know, I'm not drawing this trail very well. You start here, you end here, and we're looking at the height. So this is the height, and here x represents the horizontal distance along the trail. So something like we got our axes here, and we're starting, from, well, really it should be, I guess, something more along the lines of this, because we're going to start there and we're going to go over. So something like this. I don't know. It's not the perfect drawing. It's good enough for our purposes. We're just starting at one side and we're going over. The x is the horizontal distance, and those little x's in my pictures, I guess I could maybe make them circles. It's the starting point and the ending point, not the variable. But here's the x-axis. We're going horizontally, and then we've got height. This is y, this is f of x. This is what f of x is telling us, it's the height. And we're walking around on some mountain here. You got your little mountain, someone planted a flag up top. It's very cool, it's fun to walk on. Let's figure out how bad of a hike this is gonna be. Is this gonna kill us? I don't know, let's find out. So here f is measured in feet above sea level, x represents horizontal distance, f of x gives us the height, and we're just looking from 0 to 5. So x is in miles. This is saying that the horizontal distance of the trail is 5 miles. Let's figure out what the average elevation of the trail is. So this is basically exactly what we're needing to figure out. We're trying to figure out, hey, we're starting at one height, we're going some other heights, we're ending at a different height, and what we want to know is, on average, how high up were we? So what we can notice is that if we graph the function, and I didn't really do that up there, but we can just pretty much figure out that we see that the trail ranges between an elevation of about 2,000 and 5,000 feet. So you can go ahead and graph this out if you want, or you can just take my word for it. But basically, all we're going to do is we're going to let the endpoints of the trail correspond to the horizontal distances a equals 0 and b equals 5, and the average elevation of the trail in feet is just going to follow exactly from our definition. We're just going to use the definition of the average value of a function. That is, f bar, the average value, is 1 over b minus a times the definite integral from a to b of f of x dx. So all we do is we plug in our stuff. We end on our interval at 5. We start at 0, so it's 1 over 5 minus 0. And then we take the definite integral from 0 to 5 of our function, which is just 60x to the third minus 650x squared plus 1200x plus 4500. So we're integrating that guy dx. All right, cool. We can run through and just do power rule, that kind of thing. Notice this is not a situation where I can use the nice symmetry properties, because my domain, 0 to 5, this is not symmetric about 0. So, all right, fair enough. But here we go, good enough. We just go through and integrate. So 60x to the third, we'll get 60 over 4x to the fourth, minus 650x squared, we'll get minus 650 over 3x to the third. 1200x, we'll get 1200 over 2x squared, and 4500 becomes 4500x, and we evaluate this guy from 0 to 5. All right, cool, easy enough. Just go on, plug it in a calculator, throw 5 in there. When you throw the 0 in there, it'll all be 0, so you might as well just throw the 5 in for x, punch it in. What you'll get out is exactly 11,875 over 3. This is probably the correct final answer to put down since it's exact. But if you just want to know, this is something like 3,958.33. So we can conclude that the average elevation of the trail is a little bit less than 3,960 feet. All right, not really that high at all if you live in Wyoming. Cool. Let's do some more. Okay, so we talked about the average value of a function. We did a kind of real world feeling example. And now let's get on to some of the theoretical implications of this concept and what it can really do for us. So, if you remember, you might be able to think of another word for average, maybe something like mean, right? Do you remember another theorem, perhaps one called the mean value theorem? Well, what we're going to do is we're going to make a mean value theorem for integrals. Basically, the idea of it is just like we drew earlier when we were looking at a function and trying to explain what the average value was. Basically, the gist of this is just that when we took our function, we drew like a quick little graph. We were going from, say, A to B. And we tried to figure out what we should do for the average value. What we came up with was some sort of like a box, right? We took a box of some height, and the height was the average value. It's got the same width, and the height is the average value, and we noticed that somehow this was achieved by going sort of like midway up the function, and that was a very bad drawing right there, so maybe something a little bit closer to this. Midway up the function, we got our average value. So this height here, h, was the average value. And notice there are a couple of places where this horizontal line at the top of the box intersects our function. What the mean value theorem for integrals is going to say is that there has to be at least one place where we intersect our function. And that's all it really is going to tell us. But this is actually kind of cool. It tells us that a function must take on its average value on an interval. And this makes sense, at least for continuous functions. So continuous functions have to do this. I should preface that. But a continuous function f on an interval from a to b has at least one point, it could have more, like the picture I drew down below. Let's call it c in the interval from a to b, such that f of c is equal to the average value of f on ab. That is, just like we drew, the horizontal line y equals f bar, y equals the average value, does intersect the graph of f for some point c and ab. So here I've got 2 points, maybe like c1 and c2, and at those points, my function is equal to its average value. There's 2 of them here, but what this is saying is that there has to at least be one. Now, continuity is super key here. If we didn't have a continuous function, such a point might not exist. And it's not at all hard to come up with examples. So I'll just sketch one out really quick. They're not even hard to do. Maybe I've got a function that's got a crazy little jump in it. You know, something like this. And, let me switch back. Maybe I'm going from, say, A over to B. I don't know, I should probably put like a hole here or something like that. Make this one filled in. These guys can go do whatever they want afterwards. I don't even care. But notice if I do something like this, then the area under the curve, which let me shade in, will be this here. And the box, which has the same area, well, it's not even very hard to see what it should be. Let me go to yellow, and just draw it in. It should be right halfway in the middle of this guy. Bada blow, there we go. So notice, this doesn't hit the function anywhere, right? I mean, this line here, right there, this line doesn't ever match up with those blue lines. It never crosses them. This function here, the function graphed in blue, isn't continuous. It's got a big old jump discontinuity, and it violates the mean value theorem for integrals. So continuity is super important. Otherwise, such a point might not exist. All right, so in its full totality, if we're just stating it formally, here's what the mean value theorem for integrals says. It says, let f be continuous on the interval from a to b, including the endpoints. Then there does exist a point c in that closed interval, such that f of c is equal to the average value of f on the interval, which by definition is just 1 over b minus a times the definite integral from a to b of f of x dx. So mean value theorem for integrals, it makes sense. Think of a continuous quantity, say speed or something like that. Think about driving your car, right? If I said I went 60 miles an hour on average for the last hour, it would be super weird if I never drove 60 miles an hour. In fact, this is saying it would be literally impossible. So it follows your natural intuition. If the average value of something, some continuously varying quantity is something, then that quantity has to be that average at least some point. So, sensible. Let's do an example and see how this works. Okay, example 13. Let's get used to dealing with the mean value theorem for integrals. So, let's find the points, maybe points, on the interval from 0 to 1, at which the function f of x equals 2x times 1 minus x is equal to its average value on the closed interval from 0 to 1. So, first thing first, let's find out what the average value of the function on the closed interval from 0 to 1 is. So, f bar, the average value, is just going to be 1 over the length of the interval, which is just 1 minus 0. That is, the length of the interval is 1, times the definite integral from 0 to 1 of 2x times 1 minus x dx. So, we just go through and we do a little bit of integration. So we can notice that 2x times 1 minus x, this part right here, this thing is just 2x minus 2x squared. So when we do an indefinite integral, we'll pick up x squared minus 2 over 3x to the third. And since evaluating a definite integral is just taking the indefinite integral and evaluating it at the endpoints, putting a minus in between, we just have to evaluate this bad boy from 0 to 1. So we plug in 1, we'll get 1 squared minus 2/3 times 1 to the third. So this is 1 minus 2/3, that's 1/3. And when I plug in 0, I'm not going to get anything. I get 0 squared minus 2/3 times 0 to the third. That's just all 0. So the average value is 1/3. All right, my function's average value on the interval from 0 to 1 is 1/3. Now, as the mean value theorem for integrals guarantees, there is some point or points in the interval from 0 to 1 at which f of x is equal to 1/3. Some points x for which f of x is equal to 1/3. This is equivalent to solving f of x minus 1/3 equals 0. And this is a good trick. So f of x minus 1/3 equals 0 will let us find these points. Let's just solve it up. Okay, so we get 2x times 1 minus x minus 1/3 equals 0. Expand this bad boy out. What? We'll get something in the neighborhood of, let's see. We'll get 2x minus 2x squared minus 1/3 equals 0. And if I do a little bit more here, I'll get, let's see, minus 2 times x squared. Let's see, minus x plus 1 over 6, something like this, equals 0. All right, and so I can take this bad boy right here. I can apply the quadratic formula. It looks real nice. I could even just apply it to this guy here if I felt like it, but this one might be a little bit easier to deal with. Whatever, it works out fine. And all we got to do, plug and chug. Use a computer if you feel like it. We already know how to do algebra, right? So we use the quadratic formula and we get two solutions. One of them is 1 minus the square root of 1/3 over 2. That's somewhere in the vicinity of 0.211. And the other one is 1 plus the square root of 1/3 over 2. And that is something in the vicinity of 0.798. Both these guys are in the closed interval from 0 to 1. They are both in there. So at these values of x, the function f is equal to its average value on the closed interval from 0 to 1. Our solutions are these two guys down here. X is 1 plus or minus the square root of 1/3 over 2. Pretty pretty straightforward, all things considered. Not that bad. Okay, cool.
Hello, Neo. Who are you? I am Isaac Newton. I created calculus. I've been waiting for you. You have many questions. Although the learning has altered your consciousness, you remain irrevocably an underclassman. Ergo, some of my answers you will understand, and some of them you will not. Concordantly, while your first question may be the most pertinent, you may or may not realize is also the most irrelevant. Is the test hard? The test is neither easy nor hard. It simply is. Your poor performance in the last exam is the eventuality of an anomaly which, despite my sincerest efforts, have been unable to eliminate from what is otherwise a harmony of mathematical precision. While it remains a burden to seditiously avoid such grades, it is not unexpected, and thus not beyond a measure of control, which has led you inexorably to me. You didn't answer my question. Oh, quite right. Interesting. That was quicker than the others.
Others? How many others? What answer?
Calculus is older than you know. I prefer counting from the emergence of one student who repeats the class to the emergence of the next, in which case this is the 6th version. There are only 2 possible explanations. Either the test was too hard, or I didn't study. Precisely. As you are undoubtedly gathering, the anomaly of poor student performance is systemic, creating fluctuations in even the most simplistic grading schemes.
You can't make me do anything. Like,
おめでとうおめでとうおめでとうおめでとう
おめでとう。
おめでとう
めでたいな。おめでとうさん。おめでとう。おめでとう。
おめでとう
おめでとう。